Thank you, ma'am, for the introduction, and it's nice to see you all. As madam said, don't tear off the plastics because she will blame me because it's it depends on whether you want to get rid of the talk. So please don't do that. And also, I am fully wired. So okay, so let's get into the stars. Now, when you look through a telescope, you see an image like this. Can anybody tell me what are things which are apparent from this figure? We can make it a bit more interactive, so you can come up and say that. What are the things that you see here? Come on, you can say. Lots of stars, colorful, blue color, red color, right? And there are many stars which are concentrated um, here, right? So this is like a blue cluster of stars, right? Now, of course, if you look at the sky through your naked eye, you won't see this many stars. It's basically because the exposure that you give to your detectors are so high that you can see even the fainter one. Do you know what is the smallest telescope that we all possess? Your eye, right? You can use it. Have you ever wondered what is the diameter of the aperture? It varies, of course, but the average aperture, you can look through the internet and see what it is. So through your naked eye, you can see maybe fifth magnitude or sixth magnitude star, but you cannot see fainter. I hope you all have had a session on telescopes and optics, right? Yeah, so you won't see this many stars at all. You see brighter stars only. And in a place like Mysore, Bangalore anyway, you forget about it. Mysore, I think you can see some stars because that may not be that much light pollution. So what we do here in astronomy, we make observations. Then in astrophysics, we apply the physics that you study into the astronomy and try to explain what we see, right? That's basic idea. Now, as once the Mark Twain, the famous novelist, said, it's lovely to live on a raft because he happened to be in a raft. We had the sky up there, all speckled with stars, and we used to lay on our back and look up at them and discuss about whether they was made or only just happened. You just wonder, right? Because the lifetime of the stars are so long that you often think that they are eternal, they are there always, right? But do are they like that? Are they been made, or can you make it? Do they get destroyed? What is the phases in which they go through? These are some of the things that curiouses us, and that's what we study. Now you might be knowing that the light takes about 8 minutes to reach to us from sun, right? Now because the velocity of the light is it's not eternal, it is a constant, right? That means the information that you seek from these celestial sources are basically coming through the light. So it is encoded in the light, and it is up to us to basically decode them and get the information about the stars that we study, right? So you all know that light is made up of several wavelengths. So now the information that is there in these wavelengths are what we are interested in. Now to get that is what we use instruments, basically spectrographs or imager or whatever information that we can get from the light or the signal that is coming to us. Unfortunately or fortunately, it is only the information that is coming to us. So You go to the nearest star, which is Proxima Centauri. It is about 4.24 light years. You can calculate in your calculation session what you mean by this. That means light takes 4.24 years. Light itself will take 4.24 years to come from Proxima Centauri. That means if something happens to Proxima Centauri today, that information you can get only after 4.24 years. That is the case with the nearest star that we are talking about. Just imagine, using a telescope, you are taking image of something like the kind of stars that I shown you. They're so far away. So what you are actually taking the picture is the picture of those stars millions of years ago, right? You're not seeing them. That is why in astronomy you can go back. You can actually go back and see what you were, if so if you are like in Proxima Centauri and somebody takes a picture from you, what actually they will see you is you as a 4.24 years younger, right? So that is the kind of information that you get. The nearest binary star, which is the Alpha Centauri A and B, 4.37 light years. The red dwarf, I'll tell you what the dwarfs are, is about 5.96 years, light years. Another red dwarf, 7.78 light years. And the nearest white dwarf, which is basically a evolved star, is about 8.58 light years. So you see, you're actually in astronomy, when we are dealing with time scales, length scales so large that you have to have a feel of what you are actually uh, dealing with. Now this, of course, is the image of the sun, and now you will be wondering, like, what is the temperature of the star? Why the star is shining, right? Why the sun is shining? Why it is spherical in shape? Why there are bright spots somewhere there? You can see these loops coming out. Why these loops are coming out? Can we explain these phenomena with the physics that we know? Are there anything that is happening inside that it is throwing away material out? So all these things are what we are actually looking at. Now, what is the color of this star? It's reddish, right? So can you guess what is the temperature of the sun would be? Like you can see, may not be this the true color. You go and look at the light, the color of the light that you see outside. What should be the wavelength? Let me just guess. What is the color of the sunlight that you see? Is it blue? Is it red? Is it yellowish? Right? What is the typical wavelength of an yellowish? Blue is what? Yeah, you are very close actually. So it is, it is about close to 6,000 Kelvin. Okay. And how will we get this? You know about the black body, right? The black body is basically the any object you heat it, it will radiate. And if it's a perfect black body, it will radiate as well as it will absorb. So whatever it absorbs, it gives away. Now there is no black body in a real black body. Everything, there is an efficiency to which something can absorb. There is a efficiency to which it can emit, right? So if you look at their spectrum, that is the brightness of the objects which are heated to certain temperature, right? Let me ask you one question. Do you radiate? Have you ever thought that do you radiate? Radiation? Where? In infrared. What would be the corresponding peak temperature? This temperature? Your MSc, right? Yeah, so I think you can say. Don't worry about, you can be wrong or anything. There's nothing like that. Forget about others who are sitting here. If you are answering, you say, I'm the only person here. Just say, okay, you can say that. So it will be close to that. So it will be in the infrared. It will be, in fact, it will be in the far infrared, right? So rattlesnakes can see infrared. That means in the night, if you cannot see things around, rattlesnakes can actually see you with the heat that you emit. Um, how many of you have seen the movie? Um, I'm forgetting it. It's an alien creature comes to comes to Earth, and then it sees Predator. Yeah, good. So so Predator, in that it sees infrared, right? And to save himself from the predator, what he does, he puts mud on his body so that it becomes cooler and it is not emitting in the wavelength in which that guy can see. So it just so our body also emits basically. So if you plot that, it will come somewhere far away here. It will peak somewhere here, right? Now, what is the function by which you can explain the curve? Explain this curve. Yeah, that is when you are looking at the peak of it, the function itself. Planck, right? It's Planck's distribution. What was the problem classically in this? Something called ultraviolet catastrophe. Must have heard about it. So what happens is, as the go to the shorter wavelength, it just shoots up, right? But later on, using quantum mechanics, it was actually solved, that problem was solved, and what you get is the Planck curve, right? Now if you integrate the Planck curve, you get the total radiation that is inside. So if you want to look at the total radiation emitted by a body which is at a temperature T, then you can just integrate from 0 to infinite, right? And how you get the Wien's displacement law? How you get the Wien's displacement law? So yeah, but how you get that expression? Huh? From Planck's doing what? If you integrate, you get the total energy. If you differentiate, what happens here? The slope. So differentiation is basically finding the slope, right? So the slope will be like this, right? What happens to the slope here? Will be 0, right? So using that, so you differentiate Planck's function and then you make the slope to be 0, that is d brightness by d lambda. You make it 0, then you can get the peak. And the beauty of this is that as the temperature increases, the peak shifts towards shorter wavelength, right? And you can see that if the temperature is high, that means it peaks in blue. If the temperature is little bit low, it peaks in yellow, and then it peaks in red. Maybe it has some connection with the temperature that you see on the stars, that they are at a different temperature, that is the surface temperature from where the light is getting emitted, and because it is of different temperatures, that it is showing you different color. So we got our first physics to explain astronomy, and the physics is very simple. Black body radiation, you look at the black body radiation, see where it peaks. So that means if I can observe this, get the right kind of information, you pick from these stars, And if I can plot a black body curve, I can actually find out what is the temperature of the star, right? Where this peak comes. Now this is only for the stars. You have enormous number of objects that you can observe when you are looking through a telescope. You can see fuzzy objects like nebulae. You don't see black hole, but you can actually infer the presence of a black hole. You can see comet. Anyway, this you can see even naked eye. Pulsars. These are pulsating stars. Basically, it sends you the pulses. They are like evolved stars. Then you can see galaxies tearing apart. You can see quasars, dark matter. Actually, it's not a matter. It's not the matter that we know. This is a completely different matter about which we have no idea. Then spiral galaxies, then star clusters, and so on and so forth. So you can see that there are so many objects, kind of objects in variety that you can see through telescope. Now our idea is basically to observe them, explain them what they are, right? There are many planets, of course you know, right? Now are there planets on other stars also? That is something which we have to look at. This is the famous pillars of formation. These are the places where stars take birth. Okay, the tips of these regions are where star formation happens. Stars are formed there, and this is something called, when we did not know about astronomy much, we used to call such a photograph as a hole in the sky, right? I'll tell you what exactly is that. You see the jets coming out of at some point at the center, and you can see that jet with a cloud like this. So this is basically a cloud, and on the tip of it you can see some jets are coming out, and these jets are actually signatures of young stars, right? And then you have this is called a planetary nebulae. You have a hot star at the center and material around it. Now this is astronomy. You look at these objects through your telescope and you see, are they all different objects, or is there a connection between these? They are all same, but you are looking at them at a different phases. For example, when an alien comes here, takes a picture of a crowd, he can see kids, he can see teenagers, he can see middle-aged people, he can see aged people, he can see female, male. Now the question is, are they all connected, or they are all different, right? So that is the basic question that you ask. Now here also it is the same thing. The variety of objects that you see in astronomy, are they all different, or they are actually piecewise things about the same thing? And that is something which we need to understand. Now you might have seen about this, right? Milky Way, where you can see a fuzzy thing with a central lane of black things. This is small and large Magellanic clouds. This is the nearest galaxy or galaxy-like object to Milky Way. Then this is the nearest galaxy that we have. Can anybody tell me what this is? Andromeda galaxy. And if you take a deep image of somewhere, of some place in the sky, you can see there are a lot of objects which are like, these are all galaxies, all of them except a few. So you can see that, from the stars you can now see, galaxies which are very, very far away. And what do you think about these galaxies? So far away that the light that might have started from these galaxies might have happened billions of years ago, that they may not even be there actually, right? And that's something which we need to appreciate. So James Webb Telescope, one of the objective was, you look at the red galaxies which the light might have started traveling from those galaxies so many years ago that we can see what was the condition when our universe formed actually. So you are looking actually behind the time. So so this we have looked at. This is basically the Planck equation. So you know that the Planck curves won't intercept, right? They cannot intercept. Uh, Two black body curves cannot intercept. That means that temperature is a unique parameter by which you can characterize a black body curve. Okay, and this is the expression. So this is the contribution from the quantum mechanics. Basically, it is a statistics that has come in, and this was the classical, the part. So this is basically the temperature at which you can, temperature as a function of, the peak as a function of temperature is basically given by the Wien's displacement law. Very simple. Okay, you know the Planck's function, you know the Wien's displacement, you can get the temperature of the star, and you integrate the entire energy which is inside, you see the total intensity or total luminosity that is given by a star or a source. The problem comes in measuring those, right? So you have to measure at each wavelength what is the radiation that is coming from the star. You put in the graph, and then you have to draw a black body curve. Now for that, what we do is we use filters. Yesterday somebody spoke about filters. Yeah, so filters are basically nothing but the glass. Because of some physical effect, they allow only a certain band of wavelengths to pass through, right? So you can get the flux that is coming from within a band. So you'll get one point here, 1, 2, 3, 4, 5 points, right? So you can get the 5 points, draw a black body curve, and you get the temperature. That means if I am designing an instrument, which can do this for the sun, and I place the, I measure this and then draw the black body curve, this would correspond to which temperature? 6000 Kelvin, right? So you can do this for any star. Again, the problem is that the stars get fainter, right? When it gets fainter, the flux that you get from these stars becomes lower. So you require bigger telescope to basically get the information, right? Now, this is the spectrum of the sun that we get, the red one, on the ground. You use a telescope, you take the spectrum of the sun, this is what you get. You can see a lot of places where, the wavelength, the energy or the light has been eaten away by something, right? Now, if you go above the atmosphere, you get this yellow one. What do you think is happening in these two? Why is that red one is so irregular and yellowish is much smoother? Yeah, so anybody else? This is on Earth, I mean on the surface of the Earth. This is above the galaxy, above the atmosphere. No, don't make it that complicated. It's basically the material that is present in the Earth's atmosphere is basically absorbing that, right? What are those? The oxygen, the carbon dioxide, predominantly the water. Water is a molecule, right? What is the characteristic of a molecular spectrum? It will not be a exactly. Excellent. It will be a band. That's exactly what is happening here. It's very, broad band. So basically, atmosphere is eating away right? So atmosphere is taking energy from the sunlight. Now we know that from conservation of energy, it cannot just take. What it does, it emits also. So the atmosphere emits this light, maybe in infrared, right? So absorption is predominantly in blue, and emission may be happening elsewhere, right? So you see that, so this actually means that if you want to get the true flux from a source, you have to go to cross the atmosphere. Otherwise, you have to calibrate. You have to have a source which you know the flux, and then you observe stars, compare the flux and correct for it. That's exactly what we do here. And this is a Planck's function of about 5250 degrees Celsius or Kelvin, doesn't matter, that is fitted with it. Now once you know how to calculate the luminosity, the color you saw there, that color and temperature can be interchanged. So because if it is a blue color, that means it is, yeah, hotter temperature, right? So you, for the time being, you take this as the temperature scale. So temperature increases as you go like this, the luminosity increases as you go like this, and you measure the luminosity and the temperature of the stars, put them in this what is called HR diagram. This is the diagram prepared by two physicists, Hertzsprung and Russell, independently, and they came up with this plot. This has lot of physics in it. Okay, yeah. That's this one, yeah. Right. So this is what you are observing, right? Now you plotted with a Planckian, a Planck function. Yeah, basically this equation. Change the temperature. Yeah, 5250. That's exactly what they have put in for this. And they could fit it. They could fit at least the red region very well. That means that the black body, you can see that it's not perfect, right? But approximately it is fitting with a Planckian, which is corresponding to this temperature. This may be because it depends on what is the resolution with which you are fitting the data also, right? Yeah, so this is like, this region, so you can see there are a lot of stars which are predominantly stars are occupying this loci, right? Then there is this, and then there is this. It is not that the entire region is filled with stars. Can you infer something from this plot? Okay, that is one point. Anybody else? Anything that you, on the road when you go, where do you see most of the vehicle? A high concentration of vehicle. Where do you see? Huh? Signal, right? That's because something is stopped. That because the the time over which that vehicle is going to be in that place is larger. That is why the concentration of stars will be higher, right? It makes very sense here also. That means these sources are going to spend most of their life time in this uh, region. So this means everywhere where you find these concentrations are the regions where star is going to spend most of its time. And this is called the main sequence, where the star burns hydrogen in its core. So it can live longer, right? Its time scale in that stage is longer. Our sun is right now burning hydrogen in its center, so that is why you can see that it's almost not changing, right? There are subtle changes, but for a layman, you look at through naked eye, nothing is changing in the sun, right? Now this is the this is called the main sequence, where these are very low mass stars, so they are redder, low mass. These are bluer, so they are hotter, and they are massive, much massive. And this is normalized to the sun's luminosity, so sun will come somewhere here, which is yellowish in color. This is a pseudo color which is given. Okay, and luminosity is basically this, and this comes from the integration of the Planckian, sigma t raised to 4, right? And this is the radius of the sun or any star. So this is the surface area of the star. So basically the energy is generated where? At the core, right? Now for nuclear reaction to take place, what is the temperature that you require? Is about 10 million Kelvin. So that is the temperature that you require for the nuclear reactions to initiate. And that temperature is coming from the mass of the star, because it is pushing, right? The very mass of the star is actually compressing the matter, and at the core the material is so compressed that temperature becomes very high, and at that temperature the nuclear reaction ignites. Can you guess what will be the smallest star that you can have, if what I said is correct? Smallest star would be an object whose mass is sufficient enough that its core pressure is high or temperature is high. If there is a lump of mass, the pressure is not that high, that gravity is not making the temperature at center very high for the nuclear reaction to happen, it is not a star. Earth, for example, that means its mass is not enough, the temperature is going to 10 million, right? Even Jupiter is no. There are other objects like black holes, which are like failed stars. Their mass is not enough that they can ignite nuclear reaction at its center, right? So this is basically the luminosity that you get, and the unit of the luminosity is watt. So it's basically power, right? Or ergs per second. What does that mean? So I say sun's power is something L. What does that mean? Ergs per second. What is happening to that energy? Is coming to us. So what is happening to the energy of the sun? It's losing. At what rate? Luminosity. So basically a star is losing its energy per second with the value that you take it here. If 1 is the energy by which sun is losing, you can see a star which is here. 1,000, 10,000 times is what the energy is it's losing. That means the lifetime of these stars will be very small, right? Because losing energy very fast. And what about these guys? They must have formed with the galaxy, our sun, right? It's quite old, right? Because the size is such that loses energy slowly that it can live longer, right? So that's particularly the. Now if I go and look at the spectrum of stars which are like bright, like sun, like very low mass, red stars, I see something, get some spectrum like this. And these are basically the black ones. So the red ones, I mean the colored ones are basically the continuum. That will tell you the temperature of the source. Whereas these lines are basically the atmosphere, the elements which are present in the atmosphere of the star absorbs the radiation which is coming towards you, and that information is given here. And this is H alpha. Do you know what H alpha is? Yeah. What are the series in hydrogen atom? Yeah. And Lyman, what is it? No, Lyman is Lyman alpha, Lyman beta, which comes in UV. And Balmer lines come in. Yeah, Balmer is basically transition 2 n equal to 2. So 3 to 2, 4 to 2, 5 to 2, right? That is what you get the Balmer. So you get Lyman in this region, Balmer in this region, and you get Passion, bracket, Pfund, right? Nothing great. Whatever you are studying in physics is what we use here, basically, right? So what you can see about, for example, H alpha, what are you inferring from the spectrum? Can you say what you are inferring from the spectrum? Right, that's very good. It's been taken off. That means the atmosphere has hydrogen in that excited state, right? That something has to be excited means what? Yeah, what is the condition by which that happens? Very good, it's the temperature basically. So it is the collision, right? So hydrogen atom is being collided with some other partner. What type of collision? Is it elastic, inelastic? It should be inelastic. Why? Right, so it increases the internal energy, right? So that is basically causing it. So what happens is that the hydrogen molecules or hydrogen atom, if it is neutral, it collides and then it gets excited and then gives you that. So it has excited, so it has gone from the continuum. That is why you see them as black, right? And then anything else? Is H alpha there everywhere? Right? So it has a slight increases, comes to maximum, goes down, down, down. It happens at which temperature? Corresponds to A0, which is about 10,000 Kelvin, right? Now you have other, you have H beta also. H beta also is maximum at there, right? H alpha, H beta, so all Balmer lines are prominent at a temperature which is this. And then you have other lines, helium neutral, helium excited. 2 means it has lost one electron. So 1 is neutral, means all the electrons are intact. It loses 1 electron, you write 2. So that means there are species where you have this H helium 2, means it is ionized helium. You have ionized hydrogen, or if you have ionized iron, you have ionized magnesium. Now the question is, why is it that some of the stars are showing that? Not all of them are showing this, right? And then you come here, you have all this, number of black lines are increasing, right? That means, as ma'am said, it's not lines anymore. They are like bands basically. That means you have what? Molecules. If you want to have molecules in an atmosphere, what should be the temperature? Should be cooler, right? So they are cooler. So you explain them now. Why is it that some of the stars, what are the conditions? So can I revert back? Here I know the temperature and I know the lines. Now if I take a star for which I have absolutely no idea, I go and take a spectrum. I find H alpha which is very, very prominent, H beta very prominent. What type of a star is that? A0, right? So that is how you classify stars. Okay. Now let us come to this the dark patch that you see in the sky. People wondered that it is a hole. I mean, actually, people thought through which you can go to other universe, right? So, but then this is taken in 0.4. That means it is invisible. 0.44 micron means 400 nanometer or 4400 angstrom. So this is basically in optical, right? Now you keep on increasing your wavelength in which you are observing. Can you see here? You can see the stars from behind. That means any material which is here, okay, what is the when is the efficient scattering of a radiation can take place by a particle? Say if I am throwing a blue light, when is it that it is efficiently scattered by any particle? Not energy level, the wavelength and the dimensions of the particle is comparable. So that means there is no scattering or absorption taking place. That means the particles which are here, are smaller than the wavelength in which I am observing. So these are not holes, but there are material present in the region, and I am now getting information about the material also. Material is not big like a rock or like a brick, but its size is comparable to or less than the wavelength in which I am looking at, right? So this means that the space between the stars, you have seen stars all around, right? The space between the stars are not actually empty. There are what is called interstellar medium. Have you seen the movie Interstellar? Right? So the interstellar region is not empty. It has material, it has gas, it has dust particles. And how do you infer from there? So how many of you have taken hydrogen spectrum? So okay, so what you do is you put a continuum and then you put a hydrogen gas, excite it, and then you take a spectrum, right? So if the temperature of the hydrogen gas is less than the continuum, what you see absorption lines, and if the temperature of the gas is high, then it will give you emission lines, right? So this is exactly what you see here. So if you have a continuum spectrum, you pass it through a gas or a cloud, what you see is there are some more lines coming in, right? Additional lines which are coming in. So these are the absorption lines, basically because the temperature of this is cooler than this continuum. Now if I look at the same thing in an angle, then I can see many of these emissions. I don't see any absorption because I am not seeing these things in the background of a bright source. So that actually, by which you can find out whether there is interstellar medium or not. There is one more thing. Now, you know that if something is going away, the emitting part thing or object is going away from you, what will happen to the radiation that is coming towards? It will be redshifted, right? And the thing which is coming towards you, it will be blue shifted. So that means in a binary star where things go round, right? Now you look at from there, you try to study this binary star which is going like this. What will happen to the spectrum when this object is going away? That will be red shifted, and the one which is coming towards you will be blue shifted. So that means the lines coming from these sources should actually modulate with the rotation period of this binary, right? But when people were studying that, they found that some of the lines which are very narrow, it's not moving at all. That means they are somewhere in between, not associated with the source that you are studying, but they are somewhere in between the, binary and us, basically. And that is how people found out that there is a interstellar, gas present in the. Now the same cloud, same hole in the sky, if you take in, say, molecular emission, you take an image of the cloud in molecular emission, you will see them very bright. So these are basically not empty. They have dust, they have gas. It's perfect. It's perfect for making stars inside these regions. And these clouds are the one which collapse to form stars inside, right? Now, how a cloud can collapse? Why it has to collapse? If you have a gas, if I say that is in hydrostatic equilibrium, means what? Gravity is basically countered by the pressure, right? So you can see that comes here, the density which internally connects to pressure and the temperature. So it's basically, if the region is cooler, the mass which can collapse will be smaller. That means smaller and smaller region can collapse to form star. Or if the density is higher and higher, right? Or combination of both. That is something which is very cool, which is highly dense. It's sometimes due to some perturbation, we don't know what is that perturbation. Maybe because of some external trigger, this hydrostatic equilibrium is lost and the cloud goes into gravitational collapse. Once gravity takes over, nothing can stop, just collapses to form a star. And this is basically the different stages through which a star formation happens. So you have this molecular clouds like the one which you saw. At some point, gravitation collapse happens. It forms a star. Now you see this cloud will have a rotation, right? Now the cloud is a big one, and now it is going into a stellar size. So initially it had an angular momentum. What will happen if a rotating girl is drawing hand inside? Spins faster, right? So the angular momentum has to be conserved, right? And that conservation happens by forming a disk. So material will not directly come onto the star, but it comes through the disk, and some of the angular momentum will be taken away by the jets that you. So that is how I showed you the picture of the jets that are coming out from the star, right? Now we can explain why is that there are jets. We don't know how the jets are launched. We know that jet is needed to take away the extra angular momentum. Now once you have a star with a disk around it and an outflow, slowly the outflow goes off as the accretion becomes smaller and smaller, and what you see is the disk which is having a lot of gaps where the planets are forming, right? So that is how you can form a solar system from basically a cloud. Now in HR diagram, where are they? So the evolution of the stars are such that you have seen that they will be on the 0 age main sequence, but these young stars are actually above the main sequence because they are arriving onto the main sequence. The nuclear reaction has not yet started in these objects. Sometime it will be. So, and that is when it actually joins to the main sequence. The place where it joins, that is when the temperature of the interior is such that the nuclear reaction initiates. Now you take a HR diagram of a cluster. Cluster means all those stars are formed out of one cloud and they are all at same age, right? So they, as they evolve, they go out of the main sequence. So these are the stars which are actually not undergoing nuclear reaction within. Now what is the type of nuclear reaction that takes place inside? The nuclear reaction that takes place inside are basically the proton-proton chain, where two protons, 2 and 2, that is 4 protons are combined together, and that gives you one helium basically, right? So you have a helium 4 atom forms out of 4 protons, and the difference in the mass is what you get basically as the energy, which is equal to mc square. I think you all know this equation, right? Now let us do a small calculation of it. So the total mass of 4 hydrogen you can put together as this, right? 4.031300013, and mass of one helium atom is this. You take difference of it. Now this is the difference in the mass, and this difference is actually giving you the energy that you all get here. Okay, now that comes to this. You divide this with this, you get 0.7. So 0.7% of the total initial matter is getting converted when one such nuclear reaction or event takes place. Now you know that mass of the sun is 2 into 10 to the power 30 kilogram, right? So energy, you can calculate it as 0.1. This 0.1 factor comes from the fact that the core is only 10% of the total sun. Okay, so that is kind of the total mass that is getting converted. So 0.1 multiplied by this factor, mc square, and the luminosity of sun, you know this, right? So basically what the energy that you get is basically the small fraction of the difference and the burning of the core that you get. Okay, and you can actually calculate to what extent the sun can live. If you divide this, this is basically the luminosity. If you can calculate the total energy and divide it by luminosity, you get the time over which our sun can live, right? And maybe you can, those who are interested can have do this calculation. This is for a star of mass of our sun. But if the mass is much bigger, then it can go even further. So you can have all other elements formed within the star, right? Do you know the carbon, the iron, magnesium, all these elements are actually formed inside the star, right? What is the element which is there in your blood? Iron. In your body? Calcium. So all these elements are actually, you all were born inside the star, right? So that is actually the implication of studying these stars. So you have low mass stars which can only burn to helium, but as you go massive, and so you need massive stars to basically produce heavy elements. And what this curve tells you, that there is a peak by which it can stop. That means beyond iron you cannot form elements inside the star, but you do see elements heavier than iron, right? Where are they formed? To curious people, you can read it, okay? But this is where it stops actually. So this is what the various the transitions that I was talking about. You have Balmer, Lyman, Balmer, Paschen, bracket, Pfund, and you can calculate the wavelengths corresponding to it using this equation. I think you all study this, right? And again, you can actually calculate what is the wavelengths of these lines corresponding to. When you look at a type star, which is about 10,000 Kelvin, what you see is spectrum like this. You have H alpha, H beta, H gamma, H delta, and then it just dies down. Why it dies down there? It just drops here, right? What happens to the Balmer when it goes to infinite? Gives you a continuum, right? So beyond that, the entire thing will be absorbed, isn't it? Because so you should not see it. So you can see the lines which are, and you can actually calculate what is the difference between them, right? And what about the strength of these lines? It depends on what? Like you said you have taken H alpha hydrogen spectrum, right? Will the strength of the lines increase with temperature? It should, because more and more hydrogen is now excited, right? And that is actually given by this equation. What is this equation? That exactly is that. So it depends on the temperature, right? And also it depends on this factor which gives you the degeneracy of those levels. So this is basically gives you the number of atoms that can go into, to the excited level. Ah, that's what I don't I don't want to tell that. Depends. Yeah, find out. Okay, remember this and find out. I don't want to tell because then you remember and then forget. Find out this. How can you find out the number of particles which are there in the excited level as a function of temperature and of course the energy difference. This is the energy difference between the two levels that you're looking at. So you can actually calculate what is the temperature that you need to take at least half of the particles or half of the hydrogen atom from the lowest or the ground state to the first excited state. What is the kind of temperature that you require? It's about 85,000. That means to take hydrogen atom from ground state to the first, you require 85,000. But you saw that Balmer lines H alpha is very strong at 10,000. What is happening here? This was a puzzle, right? So the thing is that we are not taking into account the ionized hydrogen. So you have to take into account Saha's ionization equation also to explain the temperature that you see. That is true. Yeah. So this is basically calculated for the hydrogen. Now you can do this for any level actually, and this is the degeneracy equation. So if you put in these and then calculate what is the temperature that you require, actually you can run a program, write a small program in Python, and you just generate all the temperature that you require, taking into account both the Stefan's-Boltzmann's equations and the Saha's ionization equation. Okay, so what all things you study, directly you put in, you can actually calculate so now you can calculate what is the numbers of hydrogen in different levels. That again gives you a very precise measure of temperature, right? Instead of colors, now you are actually looking at the elemental information and directly calculating it. Now this is the Saha's ionization equation, so it gives you what are the number of atoms that have gone from neutral to ionized, and once you know that ratio, you can actually calculate. So the ratio of ionized to total as a function of temperature, the half of them happens 9600, exactly where you see A0 type stars, the maximum Balmer line. Basically that information comes from here. You can calculate two equations, put in with the information about temperature and the knowledge of that atomic physics. We can calculate what is the kind of temperature is there. You can do this for any element. This is what the bands that I was talking about for a cooler star. What is the kind of bands that you see? Okay, again, now if you can actually, sorry for this, you can calculate the age in which the age of the stars which it spends in each of this this phases by calculating the total energy and the luminosity. Not going to that. And this I have spoken about. If you are two stars in binary, then there will be a change in the lines, right? And if you know what is the shift, so this is basically the region where it should not. It's the rest wavelength, right? Now as the star moves, these lines can shift, can blue shift, it can red shift, and from the shift that it has, and what is the line that you are looking at. For example, if it is H alpha, and you know what is the velocity, you can actually calculate what is the velocity with which two of them are, right? So that is the information that you get from there. And spectrum can also give you information about the redshift. The galaxies are receding away, right? Just imagine if you have a galaxy where you have a O-type star, you can resolve it, okay? And galaxies receding away because your universe is expanding, right? That means what will happen if you take a O-type star, which will be reasonably brighter, right? So you can look at it far away, and you make it shift at different redshifts. Redshift means it is expanding at different extents. What will happen to the spectrum? The spectrum also will move its position. So now if you want to calculate the redshift or the expansion of a certain length of thing, what you need to do? You take a spectrum, see where this other lines may be difficult to measure, but actually you can see this break, right? How do you get this break? You get this break. Why is it that a O star has a break here? Very good, because it's a continuum. Why it's happening? What is this line? H alpha. What will be this? Is the break, Balmer break, which you are. So that you can uniquely, identify in a spectrum, and you can actually see where it is moving. So by taking a spectrum of a galaxy, you can actually see how it is receding. And there is a well-known equation where you can actually calculate the distance of that galaxy from the receding velocity, and you can actually study about the galaxies also. So spectrum gives you a lot of information, not only about the star themselves, but of the universe as well, right? Yeah, I think I'll stop here and take the class questions if you have. I'll ask. Anything if you have anything. I know many of you have questions, but you're not asking because of that barrier. But I think don't worry about it. Anything that you want to about stars. Okay. Yeah. Right. No, so continuum, for example, when you take continuum spectrum and you take a cut, right, at some color it should peak. What will be that peak? It depends on the temperature basically. Yeah. Ah. Yeah, this one. I didn't get the question. What is the question? Yeah, so it's everything is embedded there. So if I take a cut like this, what I will be, yeah. So if I take a cut, what will happen is, if I take this, say brightness, right? Brightness in that spectrum, and as a function of wavelength, because it is at different colors, right? Now it will not be this, it will be this, right? With the lines that you're seeing over there, that means it will be like this. So I can use these lines which will be much precise, or if I don't have, I am a poor person, I don't have a spectrograph, I can actually use the filters, get 5 points, and then I can get. So I use the filters, get these points, and then you fit a plank and then see where is the peak. But that will not be that precise. If you want a precise estimation, then I need to go and get with the spectrum basically. If I can get two lines of same species, say hydrogen atom, I can have H alpha and H beta. Then I can calculate based on the equivalent bit, the basically the depth in which the flux has been taken.